Hello and welcome back. So in this video I want to basically show you how basically the voltage in a RC circuit is basically leading or lagging, and the whole story behind that. But before doing that, I need to tell you all about the RC circuits and basically how the voltage is leading or lagging. So let's do a couple. Let me first tell you a little bit about these circuits, and then we will get to the rest of the things. So basically what an RC circuit is that you have basically these are you could have actually something like you could have a circuit like this, meaning that you could have a resistor over here, and then actually you could have a capacitor over here, and then a resistor over here, and then this resistor goes to ground, and then this becomes your V of in, and this becomes your basically V of out. And then you use this in an AC circuit. You use this as some sort of voltage divider or a filter. What that means is that here you will have usually a signal generator or some sort of sine wave signal going in, and then so this is basically an AC signal going in, and then basically usually based on the frequency of this signal you will have some sort of voltage over here. It's just like a simple, for example, a simple resistor network or resistor circuit where you have basically, for example, two resistors over here, goes to a power supply, and let's say that this is V of S, and this is R1 and R2, and you can and this sort of circuit you usually use it as some sort of voltage divider. You will have some voltage dropped across R1, which you can call V of R1, for example, some voltage dropped across R2, which you can call V of R2, and you use this for different kinds of purposes in your circuits, right? So in basically AC circuits where the frequency is changing, you use this kind of circuit in order to use some sort of filter, and then this is called basically this is called depending on depending on how you build the circuit, it's either called a high pass filter or a low pass filter. So you have basically either a high pass filter or a low pass filter. So what a high pass filter is, basically you have let's have the same circuit over here. So this circuit over here, as you can see, there is a capacitor over here C, and there is a resistor over here R, and this is the input signal, this is the output signal. So and the output signal is, of course, is some sort of a sine wave over here as well. So if you have the graph of the frequency, the input frequency of this circuit over here versus this V of out, which by the way is also the voltage across this resistor as well. What happens is that as you increase your frequency over here, the reactance of this capacitor is going to decrease. because well, you know that the x of c, or the reactance of that capacitor, is 1 over 2 pi fc. So since c is in the denominator here, since f is in the denominator, the more that you increase your frequency, the lower is going to be the value of this reactance over here. They have some sort of indirect relationship. There is some sort of indirect relationship between the frequency and the reactance of the capacitor. So what happens is that as you increase the frequency, the capacitance is going to decrease. So the capacitance is going to decrease, and so you're increasing the frequency, the capacitance here is decreasing. That means that the voltage drop across this capacitor is decreasing, and so the more voltage is going to be dropped across this resistor. So that means that the voltage over here is going to get to increase and increase more and more, and that's basically your output voltage over here. So that means that as you increase your frequency, the output voltage over here is increasing, and that is basically this thing over there. It would look like something like this until you reach some specific frequency over here, and then you will have some sort of voltage very near the very close to the supply voltage over here, and that's called a high pass filter. That's called a high pass filter. And it's been called a high pass filter because, as you can see, at higher frequencies, a larger portion of your signal is passing through the filter. At lower frequencies, a larger portion of your signal is being suppressed and not passing through the filter. So for the same reason, it's been called a high pass filter. So we already talked about this one. Now about a low pass filter, what happens is that you have a circuit, you have basically the same RC circuit, but then you have to swap your R and C, meaning that you put your R over here, and then your C comes over here, goes to ground, and this is then your V of out, and this is actually the V across the capacitor over here, and this is your resistor. And so what happens over here is that this is your V of in, and this is some sort of sine wave, and you'll get some sort of sine wave over here as well. They're going to be different in amplitude. So then what happens here again, as you let's say that this is F of in, the input frequency here, and this is your V of out, this voltage across the capacitor over here. And as you increase your frequency over here, the reactance of this capacitor is going to decrease. So we said that over here, since the frequency is in the denominator here, the more that you increase it, the more you're going to decrease the reactance of that capacitor. So with increasing the frequency, the reactance of this capacitor is going to decrease, and so the lower voltage is going to, the less and less voltage is going to be dropped across this capacitor, and more voltage is going to be dropped across this resistor up here. And so with increasing the frequency, the voltage is actually dropping. That means that in the beginning, at very low, basically frequencies like 10-20 hertz or something like that, the voltage is going to be like this, and then it's going to drop, and then it's get very close to ground over here, something like this, and so forth. That's basically called a low pass filter. That's basically called a low pass filter. Okay, so this low pass filter over here, what it's been called a low pass filter because, as you can see, at very low frequencies most of your signal is passing through, and then at high frequencies most of your signal is being suppressed and not really passing through the filter, meaning that over here the output voltage is very close to the supply voltage. Over here the output voltage is very close to the ground. So that's basically why it's called a low pass filter. And of course, you know that this voltage you can control it with the frequency that you're providing to the circuit. Now there are many different characteristics of these circuits, but what I wanted to basically discuss in this particular video is the fact that, of course, in these circuits, you have basically something. You have the input voltage, and I want to basically specifically now talk about this circuit up here, which is a high pass filter, and you have this resistor over here that is connected to ground. And what happens over here is that you have your input voltage, you have this output voltage, which is the voltage across the resistor. And what happens in this circuit is that the voltage across this resistor, of course, it's going to be depending on the frequency over here, it's going to be very close to ground or very close to the supply voltage. It's going to change over different values of frequency, but what happens if you actually try to do this on for example, using a signal generator and a few capacitors and things like that, and some resistors, what you will find out is that this output voltage is then going to lead this input voltage by basically different values depending on your frequency, and depending on the value of this resistor, and depending on the value of this capacitor. So that I wanted to show you in this video. So basically what you can do in this, what we want to do in this circuit is that, first of all, there is a couple more things that we need to discuss still. So there is something in this context. There is also something that we need to talk about, and that's called the Phasor diagram. So a Phasor diagram is basically a diagram that shows you some relationship between the voltage across this resistor, the voltage across this capacitor, and also the input voltage, and also the current that is going through the circuit, right? So, and that is and for that kind of purpose you need to use it's called a Phasor diagram. It's called a Phasor diagram. And for that you are going to use a simple, it's some sort of simple vector diagram that you have most probably, hopefully, of course, studied in mathematics. So what a phasor diagram in this, how a phasor diagram or vector diagram in this context, how that's used, is that you have this basically this vector over here is the voltage across the resistor. This voltage here is the voltage across the capacitor, and if you construct some sort of square, this voltage over here, this vector over here, refers to the input voltage, and this vector over here is the current going through the circuit. Now, if you come back to this circuit over here, you can see that in the case of this phasor diagram, so this V of R refers to this V of R refers to the voltage across this resistor. No, I'm sorry. No, I'm sorry, over here. Okay, so this V of R refers to the voltage across this resistor. This V of C refers to the voltage across this capacitor. That, well, of course you cannot measure using an oscilloscope, because then you would ground your resistor, and then you would basically somehow mess with the whole circuit. So I don't really know if it's possible to measure the voltage across this capacitor using an oscilloscope, because the two leads on an oscilloscope are basically grounded, and so you cannot actually do that if you were to use both of your channels on the oscilloscope. But anyway, this phasor diagram, V of C refers to the voltage over here, and this vector over here, V of N, refers to the input voltage over here, and then this vector over here refers to the current going through this series circuit. This is a RC series circuit. Now, what happens here, for example, here you have some angle over here between the V of R and V of N. You can call that, for example, theta, and there is some angle over here between V of N and V of C. You can call that, for example, phi. And in this phasor diagram, as you can see right now, V of R is actually leading V of N, and V of N is actually leading V of C. Or in other words, you can say that V of N is lagging V of R, and V of C is lagging V of N. That you can say that in both ways. So we are specifically talking about leading and lagging signals, AC signals, meaning that compared to V of N, V of R is actually leading, and compared to V of R, V of N is actually lagging, right? Or if you were talking about V of C and V of N, then compared to V of C, V of N would be leading. Compared to V of N, V of C would be lagging, right? Okay, so of course, if you didn't understand this part, I'm going to show you on the oscilloscope what that actually means in terms of two signals being compared on an oscilloscope. So now basically this angle between, for example, V of R and V of N, that you can of course calculate. I'm going to calculate one of these for you, and I have actually created some circuit over here, so I could measure all of these on a live circuit, and I hope that it doesn't fall apart. So the formula that you can use in order to calculate this angle theta, for example, is so first of all, you know that this is a right triangle over here. So in this right triangle, well, some notes about trigonometry. So let's say that if this is a right triangle, from trigonometry, you know that if this is theta and this is, for example, ABC, you know that sine theta is equal to AB2 is going to be equal to the opposite side to the hypotenuse of this triangle, meaning AB to BC. I'm sorry, AB to AC, and cos theta is equal to adjacent to hypotenuse, which means BC to AC, and tan theta is equal to sine theta by cos theta, which is equal to these two ratios. So we are specifically talking about AB to AC to BC to AC, and these two will cancel out, so you will have AB to BC, and AB is basically this side over here, BC is this side over here, so that means that the tangent of this angle is going to be the opposite side divided by the adjacent side. So basically then tan of some angle is opposite by adjacent, right? So then what happens here is that tan of this angle theta is equal to opposite by adjacent, meaning that the opposite would be this distance over here, which is equal to V of C. So tan of theta would be equal to the opposite side, which is equal to this side, which is V of C, to the adjacent, which is basically V of R. Okay, and that is equal to, well, of course you can derive the formula, some sort of formula for yourself, and that would be a lengthy process. I'm going to give you a formula that's going to make your life much easier, and the formula is 1 over 2 pi FRC, and you can also use the formula x of C to R. So you can use these two formulas. You can either use 1 over 2 pi FRC or x of C to R. Depending on situation, you can use these two formulas. Now let's say that you have, for example, some circuit over here. Let's say that you have some circuit over here. And I'm actually giving you the values related to the circuit that I'm about to show you. So I'm going to set up my signal generator, the input voltage peak to peak. We have 20 volts peak to peak, and the value of the capacitor that I'm using is 0.01 microfarad, and the value of the resistor that I'm using is 1 kilo ohm. Okay, and the frequency that I'm running the circuit at is 1.5 kilohertz. Okay, so I have these values, and based on these values I want to calculate what sort of theta I'm going to have between V of R and V of E. So we said that tan theta is equal to V of C to V of R, and also tan theta is equal to 1 over 2 pi 1 over 2 pi FRC. So this is equal to, I don't know, 1 over 2 pi times F, which is 1.5 kilohertz, so that's 1.5 times 10 raised to the power 3 hertz, times R, which is 1 kilo ohm, so that's 10 raised to the power 3 ohm, that's 1000 ohm, and then C, which is 0.01 microfarad, times 0.01 into 10 raised to the power negative 6 farad. So 10 raised to the power negative 6 you can cancel out with these two, and then you will have 0.01 times 1.5, which is equal to, so this is equal to 1 over 2 pi times 0.015. To use a calculator to calculate this, that will give you 1 over 2 pi times 0.15, going to give you 10.61, whatever that the value is. I'm not going to, I will just simply use it in the next step. So now this is tan of theta. So now theta is equal to the tan inverse of this value, tan inverse of 1 over 2 pi times 0.015, the tan inverse of this value. So if I calculate the tan inverse of that value that I just got, it's 84.615, for example, 84.62 degrees. So it's equal to 84.62 degrees. That's theta. So now that's the angle, that's the what do you call this thing? The phase angle. That is the phase angle by which V of R is leading V of in. And now we are going to see what's going to happen to the circuit, and this is the circuit that we want to build. This circuit up here, so I have this, circuit over here. I will disconnect everything so that you can see. Okay, so I have taken this as my positive and negative rail, given this to positive and negative rail, and this is the capacitor that I'm using, and this is the resistor that I'm using. This is a 0.01 microfarad capacitor. This is a 1 kilo ohm resistor, and so you see this, the capacitor, the input voltage goes to the capacitor. So I connect the capacitor to the positive rail somewhere over here. Okay, and then the other end of this capacitor goes to the resistor, and then the resistor goes to ground. So I connect the other end of this capacitor to the resistor, and then the resistor goes to ground. So that's basically this circuit over here. I just built it over here. And now this I'm going to give to the positive and negative. Of course it's an AC signal, but you still have the ground, so I'm taking this black wire as the ground, and this as the signal. So the signal is coming from my signal generator, which is basically, now this is the ground, so I'm just going to give it to the ground, and this is the signal over here going in. Now I have my oscilloscope up here, And these are the two channels of my oscilloscope. This is channel 1, this is channel 2. I want to use channel 1 to monitor my input, so so this is ground basically over here. This is ground, and my input is basically this. My input is basically this capacitor here. So this is the input signal. The output signal, which is basically this point over here, is actually where the capacitor is connected to the resistor, which is basically this point. And then the other lead I have to connect to ground as well. Okay. And now if I go to, and I have set my basically I have set the, let me take care of this camera. Okay. Now you see this thing over here, this is the signal generator. I have set it to 1.5 kilohertz. As you can probably see, this counter over here is reading 1.507 kilohertz, and this is channel 1 on the oscilloscope. This is channel 1 up here. This is channel 2, which is basically the output. This is the output, this is the input. So you see over here I'm reading, what I'm reading is, so this is my input, as you can see. So this is my input, which is basically, channel 1 is set to 5 volts per division. So this is 1, 2, 3, 4 divisions, 5 times 4 times 1, 2, 3, 4, 4 times. So it's equal to 20 volts as we calculated as we had in our circuit. So that's 20 volts. And let me see, we have over here, I don't. Okay. So as we said that the input voltage was 20 volts, which is basically this voltage over here. You can read 4 divisions over here. 4 times 5 is equal to 20 volts. The output voltage, which is this voltage over here, is also now basically that is around 2 volts right now. The output is around 2 volts. This is 1 volt, so 2 times 1 is equal to 2 volts. And the circuit that I have, actually the circuit that we used here was this circuit over here. The circuit was actually this circuit over here. Was this circuit over here. It was a high pass filter, and you see at 1.5 kilohertz the voltage is not that high, so it's around 1 times it's around 2 volts. If I increase the frequency over here, then the voltage will start increasing. You see over here, the input is remaining this. The amplitude of the input is remaining the same, but the voltage on the output is increasing as I'm increasing the frequency. Okay. So I go back to 1.5. Okay, so this is now 1.5 kilohertz, the frequency here. So So now what you can see here, what we want to do is specifically talk about the phase angle of 84.62 degrees that we talked about here. So you see over here there is, if you move this up here, you see that they're not in phase. These two signals are not in phase. So this is the output signal over here, and this up here is the input signal, and you see that the output signal is actually not in phase with the input signal. It's actually leading. The output signal is leading, right? It's first what you can see, first you can see the input signal, and then after the input signal first you can see the output signal. So the output signal is before the input signal, and then you can see the input signal. So what that means that is the output signal is actually leading, comes before the input signal. So then what you want to do on a digital oscilloscope, you would probably be able to actually see the phase difference between these two signals, but on an analog oscilloscope, how you can actually calculate that is that you need to know on this scale, the way that your signals are basically laid out, what is what on this in this particular situation. So I can basically ground this thing over here, channel 1, and ground it, and you can see that this line is lined up right here. So, and you can see that this thing over here, that this input signal over here is, so for example, you can go for, this is one starting from here all the way up to here. This is one complete cycle, starting from here all the way up to here, down here, and up here all the way up to here. This is one complete cycle. And one complete cycle happens in, if I play with this a little bit, you see that one complete cycle happens in 1, 2, 3 point, for example, 3.2, 3.4 horizontal units. So 1, 2, 3, and 3.4 horizontal units. That means that half of that cycle is actually occurring in 3.4. So that's 3.4 divided by 2 is 1.7, is 1.7 horizontal units. Now, so that means that 1.7 horizontal units here is actually equal to 180 degrees, because the whole sine wave is actually occurring in 360 degrees, meaning that from the very beginning of this cycle to the end of this cycle, that is 360 degrees. So half of that would be 180 degrees, and half of that is actually 1.2, 4, and 6, 1.7 horizontal units. That means that 1.7 horizontal units on this scale here, where I have my signals, is actually 180 degrees, right? Okay. So now if I move my output signal up here, what you can see is that this output signal is actually so I'm going to move this. I'm going to move this exactly on this line, okay, and then unground it, okay, and then I'm going to move this a little bit, see over here, Now the difference between these two signals, for example, any point on this scale, if you take a look at this, you see that, for example, this cycle starts here, ends here, and this cycle starts here, and there is this very little difference, there is very little distance between these two, between the output and the input, and that is around 0, basically 1, 2, 0.2, 0.4, 0.6, and 0.8 horizontal units. Now 0.8 horizontal units is so I said that basically I said that 1.7 horizontal units 1.7 horizontal units corresponds to 180 degrees. So 0.8 horizontal units is going to correspond to 0.8 times 180 divided by 1.7, which is equal to 84.7 degrees. 84.7 degrees, which is exactly what we got in the calculation that we did before. Okay, so that's basically how you what the meaning of phase angle is. And I couldn't actually find a good guide on the internet, so I thought I would actually share this with you in case you want to basically either calculate your phase angle or basically measure it on an analog oscilloscope. I don't have any digital oscilloscopes. I don't know really, but I would guess probably if you had a digital oscilloscope, the digital oscilloscope would do all of these math related things for you. But an analog oscilloscope, you would have to do a whole lot of thinking in order to, and do a whole lot of math in order to get different things done. Okay, so I hope that you enjoyed this video, and thank you for watching. Thank you.